Hi everyone, I am happy to give a presentation on conditional and relative stability analysis using Nyquist stability criterion, which is lecture 14 in control systems lecture series. Of course, this is the continuation of the polar plot and stability analysis. The learning objectives of this presentation are to investigate the effect of parameter variation on stability, that is conditional stability, which we have seen in the time domain analysis, that is in the route stability criterion and then root locus. So effect of parameter variation on stability of the closed loop system using Nyquist stability criterion. So here we are going to discuss with respect to the Nyquist stability criterion. So how the parameter variation is going to affect the stability, that we are going to discuss and investigate. The second objective is to measure relative stability, that is gain margin and phase margin of the closed loop system using Nyquist stability criterion. So this is very important to understand the performance of the system. So to understand this particular presentation, let us start with the problem, because we are already conversant with Nyquist stability criterion in the previous lecture. The open loop transfer function of a feedback system is given by g of s h of s equal to k into 1 plus 0.5s into s plus 1 divided by 1 plus 10s into s minus 1. So here we are able to find that one k is in the numerator. The question is determine the range of k for stability. So what is the range of k for system to be stable? This we have to find out by Nyquist stability criterion. So the first step is to write the sinusoidal transfer function as usual, that is by putting s is equal to j omega, then finding the magnitude and phase angle. So the magnitude we know root of real part square plus imaginary part square for each complex factor. This is root of 1 plus omega square, this is again root of 1 plus omega square, they will cancel each other. Therefore k into root of 1 plus 0.25 omega square divided by root of 1 plus 10 means 100 omega square. Then phase angle is tan inverse of 0.5 omega plus tan inverse of omega minus tan inverse of 10 omega. This will be 180 minus tan inverse of omega. With the minus sign you will have minus 180 tan inverse of omega. So minus of minus tan inverse of omega, tan inverse of omega. Already there is a tan inverse of omega, so 2 tan inverse of omega. So this 1 plus j omega tan inverse of omega. This minus 1 plus j omega is 180 minus tan inverse of omega, because the point is in the second quadrant. This we have already seen in the previous presentation also. Whenever the point is in the second quadrant, 180 minus angle we have to do. So 180 minus tan inverse of omega, already you have a negative because this is in the denominator. So tan inverse of omega minus of minus tan inverse of omega, 2 tan inverse omega, that minus 180 is this minus 180, right? So as omega is vary from 0 to infinity, how the magnitude and phase angle they can vary, that we can find out. But what is very important is we should find out the range of k for stability. That means we should find out the mapping of the Nyquist contour from S plane to g of s h of s plane. So Nyquist contour has got 3 segments, C1, C2 and C3. C1 is nothing but your j omega, where omega varies from 0 to infinity. Therefore that will be a polar plot. C2 is minus j omega. Therefore C1 and C2 are complex conjugates. So C2, what mapping of C2 is nothing but mirror image of C1. That is what written here. Now mapping of C3 we should see. So what is mapping of C3? This radius is infinite radius, we know. Angle phi, already these things we have seen in the previous presentation. So we put s is equal to r into e power j phi in this expression. So k into 1 plus 0.5 r e power j phi plus 1 plus r e power j phi divided by 1 plus 10 r e power j phi then minus 1 plus r e power j phi. We have just rearranged. So here we have to substitute r as infinity because this is infinite radius r, phi varying from plus 90 to minus 90 to plus 90. So we'll have to see how this particular mapping is going to be done. See, when we substitute r e power j phi and take r e power j phi outside here on r e power j phi, here on r e power j phi, so r square e power j2 phi, here again r e power j phi, r e power j phi, when you take outside r square e power j2 phi, so they will cancel with each other. Therefore, as r tends to infinity, this term will be 0, 1 by r e power j phi, and this will be 0.5, this will be 1 by r e power j phi 0, this will be 1, so this is 1 by r e power j phi, this will be 10, this is minus 1 by r e power j phi, and this will be 1. So wherever we have divided by r e power j phi, there we will get 0. So therefore this is 0 plus 0.5, 0 plus 1, 0 plus 10, 0 plus 1. So if we simplify, we will get 0.05k. Therefore, as r tends to infinity and phi varying from, actually phi varies from plus 90 to minus 90, because here the angle is plus 90, because it varies from here to here, plus 90 to minus 90. So that change we have to make. So phi varying from plus 90 to minus 90, but that is not a problem at all, because as r tends to infinity, anyway the outside terms are going to be 0, cancelling each other, and inside, as I said, 0 plus 0.5, 0 plus 1, 0 plus 10, 0 plus 1. So finally when we simplify, 0.05k. That means this infinite radius arc, where phi varying from plus 90 to minus 90, that means many points, infinite number of points are mapped to a single point, 0.05k. So this is what we call many to one mapping. So many points are mapped onto single point, 0.05k. Right. So therefore mapping of C1 is polar product. Therefore we should do C1. C1 is nothing but we can obtain from this table, as omega is varied from 0 to infinity. So we will get minus 180 to 0 degree variation, magnitude varying from infinity to 0.05k. Here we can note down one more thing. Whatever be the magnitude at 0.05k, that is going to be g of s, h of s, corresponding to the mapping of C3. Or I can say mapping of C3 from S plane to G of S, H of S plane is nothing but this particular 0.05k. This holds good for any problem. Suppose we have magnitude 0 at omega infinity, means it will be origin. That is what we have seen in the previous presentation. One problem we have seen like that. Right. So magnitude varying from infinity to 0.05k, phase angle vary from minus 180 to 0 degree. Since we have zeros as well as poles and pole in right of S plane, there is a possibility that it goes from minus 180 to minus 210. Again it is coming back to minus 180. To exactly find out where it cuts minus 180 degree, we have to equate the phase angle expression to minus 180 degree. So that is how to find point of intersection of polar plot with the negative imaginary axis. The phase angle expression is equal to minus 180 degree. The entire thing is equal to minus 180 degree. Here one tan inverse of omega is brought to the other side. Minus 180, minus 180, they will cancel each other. So when we take tangent on both sides, so tan of A plus B formula, tan A plus tan B by 1 minus tan A tan B. Here tan of A minus B formula, tan A minus tan B by 1 plus tan A tan B. So 0.5 omega plus omega is tan A plus tan B, 1.5 omega divided by 1 minus tan A tan B, 0.5 omega into omega, so 0.5 omega square. So here again tan of A minus B, tan A minus tan B. So 10 omega minus omega, 9 omega, divided by 1 plus tan A tan B, 10 omega into omega, 10 omega square. So if we cross multiply, we will get like this. Simplify, we will get omega as 0.62 radian per second. So if we find the phase angle at 0.62 radian per second, we can verify that this is minus 180 degree. So at this value of 0.62 radian per second, if we calculate the magnitude is 0.166 K. So for which we should substitute this omega in this expression. So if we substitute and simplify, we will get this. So why this is very, very important is, always in any Nyquist problem where it intersects the negative real axis is only important, because we have to see the encirclement of minus 1 plus j0, which is happening in the negative real axis. So when omega equal to 0, magnitude infinity minus phase angle minus 180 degree. When omega equal to infinity, 0.05 K, and actually when omega is equal to 0, when omega equal to 0, the magnitude is actually K. I think I have made a mistake. So I should write here, yeah. Now it's okay. So when omega equal to 0, when we substitute, so K by K into root of 1 plus 0 by 1 plus 0, so it is K. So when omega equal to 0, K angle minus 180 degree, that means minus K. Somewhere I have marked. Now as omega is increased, magnitude decreases, but phase angle goes in the negative direction, that means more negative. Therefore this region, second quadrant, is minus 180 to minus 270. So it initially goes like this up to minus 192 or somewhere. Thereafter, after 0.5, exactly at omega equal to 0.62, this minus 180 to this variation, that means second quadrant variation, finally it converges to minus 180. Then again it goes to the third quadrant, wherein you get minus 180 degree. Thereafter again magnitude is decreasing. See, phase angle is decreasing in the negative direction. That means this is in this quadrant up to minus 90. Thereafter it is again decreasing. When omega equal to infinity, it is 0.05 K. Therefore I can say this red region, that is this region is mapping of C1. So what is mapping of C2? Mirror image of this. So this is the mapping of C2. Actually it is drawn with the discontinuous lines. So for the clarity, I have highlighted with the red color, that's all. So this is G of minus j omega, H of minus j omega, that is mapping of this C2. So I think I have explained how this comes. Once again I will explain. So as omega is increased, magnitude decreases from K to 0.05 K, but phase angle goes here, that is second quadrant, because we get this minus 215 and all. Then it again becomes minus 180 at omega equal to 0.62, wherein the magnitude is 0.166 K. Thereafter magnitude as usual decreases, and phase angle also decreases in the negative direction. So finally it converges to 0.05 K at omega equal to infinity. Thereafter what I am doing is I am taking the mirror image of this. So now the direction is 0 to infinity, because we have to map from 0 to infinity, this mapping. So this mapping is this. Then mapping of this we know is same as this, that is this point. Thereafter mapping of C2, that is from here to here, that means this to this direction. So minus K minus 0.16 is K, 0.05 K. Anyway, we will analyze the range of K for stability in the next slide. So same thing has been put for better clarity. We know very well that there is one pole in the right half of S plane, that is S is equal to 1. One pole of G of S, H of S present in the right half of S plane. Therefore, if the system has to be stable, there should be one anti-clockwise encirclement or counterclockwise encirclement of G of S, H of S contour. That is what mentioned here, because according to Nyquist stability criterion, for the system to be stable, G of S, H of S contour should encircle minus 1 plus J0 as many times as the right half S plane poles. Now there is one pole in the right half of S plane. S is equal to 1. Therefore, it has to encircle once in counterclockwise direction. Now, there are 2 points on the negative real axis. Suppose we take k as greater than 6. If k is exactly 6, this is minus 1. This will be minus 6. Let us say k is greater than 6, something around 10. Means this will be minus 1.67 and this will be your minus 10. So minus 1.67 is this point, means minus 1 will be somewhere here. So if minus 1 is somewhere here, means there is one anti-clockwise encirclement of G of S, H of S contour about minus 1 plus J0. So therefore there is one anti-clockwise encirclement, system is stable in that case. Anyway, we are not bothered about this because this encirclement is coming outside that minus 1. So we are not bothered about that when k is greater than 6. Let us consider other two cases, k less than 6. Suppose k is greater than 1 but less than 6. For example, let us take k is equal to 2. In that case, this will be minus 2. This will be minus 0.32. So therefore, this is minus 0.32. This is minus 2, means minus 1 will be here. Therefore, we have to forget about this because minus 1 is this side. So this is minus 2. This is minus 0.32. One clockwise encirclement of G of S, H of S contour about minus 1. That means what does it mean? One clockwise encirclement means, according to principle of argument, Z minus number of poles in right half of S plane is 1. One clockwise encirclement means minus 2 pi. So Z minus 1 into minus 2 pi is minus 2 pi according to principle of argument, Z minus P. Now number of zeros of 1 plus G of S, H of S should be equal to, in this case 2, because 2 minus 1 into minus 2 pi only is minus 2 pi. That means 2 zeros of 1 plus G of S, H of S are present in right half of S plane, system is unstable. Whereas in the first case, when k greater than 6, one anti-clockwise encirclement, that means Z minus 1 into minus 2 pi equal to anti-clockwise means plus angle, positive angle. So plus 2 pi. That is why Z is 0. 0 minus 1 into minus 2 pi is plus 2 pi. So no zeros in the right half of S plane. Therefore, they are not enclosed by the Nyquist contour. System is stable. Right. So here Z is 2. That means 2 zeros of 1 plus G of S, H of S are 2 closed loop poles or 2 roots of characteristic equation are present right half of S plane. System is unstable. Suppose k is less than 1. For example, let us say k as minus 0.8. K is equal to 0.8. So this will be still lesser. Therefore, this also will not be encircled. This also will not be encircled by minus 1 plus J0 because minus 1 will be somewhere here when k is less than 1. Therefore, no encirclement at all. No encirclement means Z minus P into minus 2 pi is 0. I have written minus 0, it is 0. So, Z minus 1 into minus 2 pi equal to 0 means here Z should be equal to 1. That means 1 0 of 1 plus G of S is G of S, H of S present right half of S plane. Therefore, system is unstable. Therefore, whenever k is less than k, there are two cases. K less than 1 means no encirclement, but there should be one anticlockwise encirclement. Therefore, system is unstable and 1 0 of 1 plus G of S, H of S present right half of S plane. When k is greater than 1 but less than 6, one encirclement in clockwise direction. Therefore, two zeros are present in right half spline. Therefore, system is stay unstable when k is less than 6. If k is greater than 6, system is stable. Another problem. So here the open loop transfer function is given, but there are two poles at origin. There are two poles at origin. We have to check whether the system is stable or not by use of Nyquist stability criterion. So as usual, we are writing sinusoidal transfer function, then magnitude, normal mathematical use of relations, then phase angle. So yes, j omega square means for j omega 90 degree, j omega square 180 degree, since in denominator minus 180 degree. So 1 plus j omega means plus tan inverse of 4 omega. This 1 plus j omega minus tan inverse of omega. 1 plus j2 omega minus tan inverse of 2 omega. Since 1, 2, these two terms are in the denominator, we have minus sign, as we have already seen in the previous slide and other problems. Now, we'll have to see the mapping of C1, mapping of C2, mapping of C3, all that. As usual, the problem actually goes from magnitude infinity to 0, because you have poles at origin. Previous case it was not 0, 0.05k. So phase angle going from minus 180 to minus 270 degree. So since I get minus 180, minus 180, minus 175, minus 174, minus 188, minus that is, I have decrease in negative, then again increase in negative. So I have a doubt whether minus 180 is cut twice. So to avoid confusion and to justify ourselves, I am equating the phase angle expression to minus 180 degree to exactly find out at what frequencies the phase angle becomes minus 180. Definitely at 0 it is minus 180. So phase angle expression equated to minus 180. Minus 180, minus 180, they cancel each other. So tan inverse of 4 omega minus tan inverse of omega I am keeping in the left hand side. This I am keeping in the right hand side. I am taking tangent on both sides. So this is tan A minus tan B formula. Tan A minus tan B by 1 plus tan A tan B. So for tan A is 4 omega, tan B is omega. So 4 omega minus omega is 3 omega. Divided by 1 plus tan A tan B. 4 omega into omega is 4 omega square. Equated to tan of tan inverse of 2 omega is 2 omega. So if I cross multiply, simplify, finally I get omega as 0.3536 radian per second. When I substitute omega as 3.3536 here, I can find out the magnitude. That magnitude is 10.56. That is why I am getting this point. So this point I have not calculated, just with the help of the calculator by making use of this expression. I have done this. From this I have done this. That's all. So mapping of C1 is polar plot, mapping of C2 is mirror image, mapping of C3 is origin as usual. But I have one more additional thing here. Let us see that. See, the Nyquist contour is C1, C3 and then C2. Here, what I have done is I have bypassed these two poles at origin by a small semicircular indent. I have already said that for principle of argument to apply, to apply the principle of argument, the function should be analytic. Function is analytic only if the function and its derivatives exist. They will exist at places other than singularities. Unfortunately, poles at origin are singularities. So the Nyquist contour should not pass through the singularity. That is why it is bypassed. So it is bypassed by a small radius epsilon. This radius is epsilon. This angle is theta. So here theta varying from minus 90 to plus 90. Here only theta varying from minus 90 to plus 90. Previous problem, phi varying from plus 90 to minus 90. So theta varying from minus 90 to plus 90. So this I have to map. Why I have to map? Because I am bypassing this. So mapping of infinite semicircular indent, it is almost like R into e power j phi, that is this infinite radius mapping, here small radius mapping, that's all. So 1 plus, we had 4s, so 1 plus 4s by that, so 1 plus 4 epsilon e power j theta by s square is epsilon square e power j 2 theta, 1 plus s 1 plus epsilon e power j theta, 1 plus 2s 1 plus 2 epsilon e power j theta. So here I am taking epsilon as a small, infinite small radius. This is infinite radius. So infinite small radius. So therefore when I am taking the limiting value, I should take epsilon as 0. Because only to bypass I have taken this. Therefore I have to take the limit epsilon into 0. Theta varying from minus 90 to plus 90. So if we substitute epsilon as 0, this will be 1, 1 plus 0. This will be 1, 1 plus 0. This will be also 1 plus 0. So 1, 1, 1. However, here I have epsilon square. Epsilon square means 1 by 0 infinity. E power j2 theta I have. Therefore, infinity angle minus 2 theta. Infinity angle minus 2 theta. So, as theta varying from minus 90 to plus 90, this minus 2 theta will vary from minus 90 into minus 2 is plus 180 and minus 2 into 90 is minus 180. Therefore, when theta varies from minus 90 to plus 90, angle varies, minus 2 theta varies from plus 180 to minus 180. That is why the small radius, infinite small radius, indent mapped into infinite radius with infinity angle 180 to infinity angle minus 180. So what is to be understood here is, when I map infinite radius from S plane to G of S plane, infinite radius is mapped onto a single point. That means many points, infinite number of points mapped onto single point. Whereas here, single point, that means 2 poles. That means 1 or 2 points, which is, that is, this is many points actually. So that I am representing like this, that, but it's a small radius. So that means small, this thing is mapped onto infinite arc radius. So that is actually the conformal mapping, significance of conformal mapping. So that is what we have marked here. So in the previous this thing, I know that magnitude infinity to 0, phase angle varying from minus 180 to minus 270 as omega varies from 0 to infinity. So as omega varies from 0 to infinity, it is like this. So it varies from minus 180 to minus 270 degree. Anyway, this minus 180 I cannot show because this will touch only at infinity. If at all I want to do it pakka, means I have to convert that into real and imaginary part, the G of S, H of S, and I can do. But that is not required because I am very much concerned about this point only, point of intersection. So, infinity to 0, so magnitude is decreasing. Of course, phase angle, there is a slight decrease, then it is increasing. Right. So this is mapping of C1. This is mapping. Mapping of C2 is this. Now there is a discontinuity between these two because of this singularity. This only is mapped to infinity angle plus 180. So this is infinity angle 180. This is infinity angle minus 180. So this radius we have to take infinity. So that is what put here. So we should assume this as infinity because we are showing infinity on a finite dimension plane. So if we see here, this is the G of S, H of S contour. So this is C1 mapping. This is C2 mapping. And C3 mapping is nothing but your origin itself. So here itself we get. That is what I said. C3 mapping will be normally the last point of C1. That is omega corresponding to infinity. So C1 mapping, that is this mapping. C3 mapping is origin. So C1 mapping, origin. Then C2 mapping. So C2 mapping is mirror image of this. Then mapping of this. What is the mapping of this? Infinite radius arc. So infinity angle plus 180 to infinity. Now I have to check how many encirclements are there. To find out that, so I should take -1. That -1 I have to draw a radial line. So if I draw a radial line, I can find out 1, 2, 2 clockwise encirclements. So there are 2 clockwise encirclements. I know very well that at omega equal to 0.3536, that is corresponding to -180 degree, the magnitude is 10.56. That means this is minus 10.56. This is minus 10.56. Therefore, -1 is inside here. Therefore, this is 1 and this is 2. So, to find out the exact number of encirclements, I have drawn a radial line from -1 to these two curves. Even I can draw like this also. So, when I draw this, my directions are like this. If both directions are aiding each other means you have to add. If one direction, for example, this is opposite means I have to cancel. Now this clockwise direction, instead if both are like this means anti-clockwise. That's all. Even if we take like this, we will get 2 clockwise. So 2 clockwise encirclement means, according to principle of argument, z minus p into -2 pi is 2 clockwise means -4 pi. Now there are no poles in the right half of S plane. There are no poles in the right half of S plane in the open loop transfer function. There are no open loop poles in the right half of S plane. So z minus p into -2 pi is -4 pi means, what should be the value of z if we see only when it is 2 into -2 pi is -4 pi. That means 2 zeros of 1 plus g of s h of s are enclosed by the Nyquist contour. That means they are present in the right half of S plane. Therefore, the system is unstable. So this problem, I have poles at origin. That is why I am getting this discontinuity. And this can also be done by this semicircular indent method. Right. Next very important thing is gain margin and phase margin, which are important measures of relative stability of closed loop system. So what is this gain margin and what is this phase margin? How they are useful for analysis of closed loop system stability? For example, let us consider this open loop transfer function. This is the open loop transfer function. So it has got one pole at origin and 2 non-zero poles and the parameter k, let us say. We know whenever you have one pole at origin and 2 non-zero poles, how to find out the the polar plot we know. So the polar plot will be from -90 degree when omega equal to 0 to -270 degree when omega equal to infinity. Similarly, magnitude will be infinity when omega is 0 and magnitude is 0 when omega equal to infinity. So -90 to -270 degree. Anyway, where this is an asymptote, if I ought to do, I have already done it in the previous lecture 13. So where I have separated this into real and imaginary parts, and I have even written that minus of t1 plus t2 or something. So that is not my aim. Therefore, -90 to, anyway, this will cut this at infinity. So -90 to -270. So it is cutting -180 degree somewhere here. Let us say that point as A. Anyway, I have not mathematically computed this. Let us say that is A, right? Now I am drawing a unit circle. That is, unit circle is a circle with unit magnitude. It intersects this polar plot at a particular point. The point where it cuts the polar plot, I am calling that as gain crossover frequency. So gain crossover frequency. At that gain crossover frequency, I am finding the phase angle, and this phase angle is nothing but the shift in phase angle between this and this negative real axis. So I am finding the phase angle phi of this. Then I am finding what is this shift. For example, I am getting minus 150 degree, let us say. Minus 150 degree phase angle of this means this will be 30 degree. That's the meaning, right? what I am doing other than this is, where it intersects the negative real axis, this is A. Now minus 1 plus J0 is somewhere here, right? Now what is this gain margin? What is the phase margin? See, according to the transfer function, let us assume that T1, T2 are positive. Therefore, no poles are present in the right half of phase plane. Of course, you have polar torsion that we can map by a semicircular and an infinite small semicircle, all that, okay. Similarly, we will get like this and we will get an infinite radius. That's a different thing, right? So, no poles are in the right half of phase plane. Therefore, there should not be encirclement of G of S H of S contour. If the encirclement should not be there, means where the polar plot intersects the negative real axis, this should be less negative than minus 1, or this point should be to the right of this. Right. Let us say this gain A. Now, if I make any effort to increase this gain A by 1 by A, what happens is, this will cut like this. That means this polar plot will come like this. So what does it mean? Stable system is becoming unstable system. No encirclement. If I multiply this A by 1 by A, it will come like this. Therefore, reciprocal of gain at this frequency is called phase crossover frequency, where it cuts the negative real axis minus 180 degree is called phase crossover frequency. Here I have mentioned phase crossover frequency. Right. So that gain I am taking the reciprocal. That means gain margin is the factor by which I have to increase the open loop gain at this phase crossover frequency to drive the system to verge of instability. Therefore, stable system, if I have to make unstable, what effort I should make at phase crossover frequency is called gain margin. That's all. Therefore, what is phase margin? For that, I have already seen the unit circle. That circle where it cuts is gain crossover frequency. I am finding the phase angle. This phase angle, if it is like this in the third quadrant, it is okay. Suppose it is like this, it is like this. That is, it is like this. Let us say it is like this. That is, when I am calculating the phase angle, I am not getting minus 150 or something. Instead, I am getting minus 190. Minus 190 means this will cut unit circle somewhere here. Therefore, it goes like this. Polar plot, instead of coming like this, that means minus 1 plus J0, it will encircle. Therefore, I have minus 150. I have to make it minus 190. Let us say unstable. Therefore, I am putting additional phase lag from minus 150 to minus 190. So additional phase lag required to be added at gain crossover frequency to drive the system to verge of instability. So for closed loop system, if the system has to be stable, gain margin should be positive dB, phase margin should be positive degrees. And we define this gain margin and phase margin only for open loop stable systems. That is, only when the poles are present in the left half of phase plane, gain margin concept and phase margin concept are applicable. Because whenever any pole is in the right half of phase plane, means if the open loop system is unstable, right half of phase plane means closed loop system, when we see the G of S H of S contour has to encircle that minus 1 plus J0. Therefore, there is no point in talking about gain margin and phase margin when the open loop system is unstable. Therefore, it is applicable only when the open loop system doesn't have poles in the right half of phase plane. So there is an example. So I have a polar origin similar to the previous problem. So draw the Nyquist plot and find out the gain margin and phase margin apart from finding the stability. Anyway, I have separated this into real and imaginary parts just to calculate the what will happen to the real part when magnitude is infinity, like the lecture 13 problems, right? So real and imaginary I have done. So magnitude is this, phase angle is this we know very well. Omega equal to 0, what is magnitude, what is phase angle, all that we can easily find out. Now I have one pole at origin, so one pole at origin, previous case two poles at origin. So C1, C3 and C2 and infinite small radius. I know mapping of C1 is polar plot, mapping of C2 is the mirror image, mapping of C3 I know definitely mapping of C3 is going to be the origin. This I know very well because number of poles is greater than the number of zeros in the open loop transfer function, or I can say always the mapping of C1 whatever extreme is there, mapping of C1 extreme is omega infinity magnitude 0, that only going to be mapping of C3, which I have already said in the previous problem also. So mapping of C1, mapping of C2, this and this. Anyway, this we have to see now. This is the special case. So S is equal to epsilon e power j theta like previous problem I have put. So for S I have put epsilon e power j theta and simplified. So theta varying from minus 90 to plus 90. So theta varying from minus 90 to plus 90. So when I put epsilon as 0, this is 2, this is 10, 400 by 2, okay, all that. So epsilon 0 means finally it is going to be infinity. And this is 0, this is, this is 2, this is 10. Anyway, 1 is 0. E power j theta means minus theta. So infinity angle minus theta, because e power j theta, numerator it goes e power minus j theta, that means angle minus theta. Therefore, as theta varies from minus 90 to plus 90, minus theta will vary from plus 90 to minus 90. That is what I said. Semicircular intent is mapped to infinite arc radius with infinity angle plus 90 to infinity angle minus 90. That means always this polar torsion, whenever I have single point in the Nyquist contour will be mapped to many points, that is singularity will be mapped to many points in G of S of a plane always. Similarly, many points like this, infinite arc radius, infinite, that will be mapped to origin or that constant. Right. So I have done for omega equal to 0 to infinity. So we have, we can put the tabular column if you want. So omega equal to 0, it is infinity. Infinity angle minus 90. Omega equal to infinity, 0 angle minus 270. So infinity we cannot have. So I have to draw. This will be parallel to this. Anyway, to find out where it touches. Anyway, that we have not done in the previous problem. That is why I have separated that into real and imaginary parts. So in this real, if I substitute here omega as 0, this is going to be infinity. This will be minus 4800 by 4 plus 0 into 100 plus 0. This is going to be minus 12. That means minus 12 plus j infinity when omega equal to 0. So minus 12 plus j infinity, that means minus 12 line will be an asymptote to this. Therefore, this line will cut minus 12 at omega equal to 0, that is at infinity. Right. So this is at minus 180. So minus 270. So how to find out this point of intersection? All that now we will see before completing the problem. So polar plot intersects the negative real axis at minus 1.9. So how to find out this minus 1.9? Very simple. So I have to find out the phase angle expression. So what is phase angle expression? Minus 90 minus this. So I can write the phase angle expression from this. Omega by 2, 0.5 omega. This is 0.1 omega. So that phase angle expression I am equated to minus 180. So take tangent on both sides. So we will get this expression. Tan, if we use the tan of A plus B formula, all that. So this is infinity means denominator is 0. So that is why denominator 0. Simplify, you will get root 20. So if you substitute this root 20, so root 20 is 4 point something. So root 20 is 4 point something. At that root 20 we have to find out the magnitude. So we have magnitude expression. Omega, you substitute root 20, we will get some magnitude. That magnitude is 1.9. Therefore this is minus 1.9. Because 1.9 angle minus 180 degree. So minus 1.9. That means it intersects the negative real axis at minus 1.9. Right. We also need gain crossover frequency. How to find out the gain crossover frequency? Because this is your phase crossover frequency, root 20. At the phase crossover frequency, I am finding the gain. That gain is 1.9 and that is minus 1.9. The point is minus 1.9 and gain is 1.9. Then I have to find out the unit circle where it intersects the unit circle, the polar plot. That is this point. So I have to equate the magnitude expression to 1. So equate the magnitude expression, this expression to 1. So equate this to 1. So squaring on both sides, cross multiplying, simplifying, all that if you do, you will get gain crossover frequency as 5.72. At that gain crossover frequency, find out this phase angle. That is, substitute omega as 5.72 in this expression. That is, in this expression it's minus 90 minus this phi expression itself. So you will get that phase angle as minus 190.49 degree. I have already said whenever the phase angle is minus 190 means that means somewhere here. Therefore this phi is here means it cuts, that means it encircles minus 1 plus j0. Therefore the system is unstable. So minus 190.49 means more negative than minus 180. Therefore minus 10.49 degrees is the phase margin. So here it cuts the negative real axis at minus 1.9. That means it has already encircled minus 1 plus j0. So the gain is here more than 1, definitely unstable. So 1 by 1.9, 1 by a 0.52. So if I want to do it in dB, 20 logarithm of this is minus 5.6. Therefore whenever this gain is more than 1 or this point is more negative than minus 1, definitely at that phase crossover frequency system will encircle minus 1 plus j0, system is unstable. Or if I get the phase angle at the gain crossover frequency as more negative than minus 180, there also it encircles minus 1 plus j0, system is unstable. Anyway, after completing this, I can complete this also. But this is mapping of C1, this is mapping of C2, mapping of C3 is origin itself, and this is infinity angle plus 90 to infinity angle minus 90. That is what I have shown here. So system is unstable. That is why gain margin is negative, phase margin is also negative. Whenever gain margin, phase margin negative means system is unstable. Here, how many encirclements if I am very much interested? Anyway, it is unstable, I know. So from minus 1, I have to draw a radial line, or even from origin I can draw the radial line. So if I draw the radial line from here, definitely it will cut these two. Cut these two and the directions are like this. Or if I draw like this also, directions are like this. So two clockwise encirclements, that means by principle of argument z minus p into minus 2 pi is 2 clockwise means minus 4 pi. 1 clockwise means minus 2 pi, therefore 2 clockwise minus 4 pi. Therefore no poles in right of S plane, because in the transfer function no pole is in the right of S plane. If the pole is in the right of S plane, then we cannot find gain margin, phase margin at all, because it is applicable only for open loop stable systems. However, z minus p into minus 2 pi equal to minus 4 pi, that relation we have to apply for this. So p is 0, so z minus 0 into minus 2 pi is minus 4 pi, means that z should be 2. Then only 2 minus 0 into minus 2 pi is minus 4 pi. Therefore, two zeros of 1 plus g of s are present in the right of S plane, system is unstable. So I think I have explained the different types of problems in Nyquist stability analysis. So we started with the conditional stability problem, range of k for stability. Then when we have two poles at origin, how to avoid that singularity by a semicircular indent, and then how one point is mapped into number of points, that is infinite small radius is mapped onto infinite radius, that I have said. Then gain margin, phase margin also I have explained very clearly. Now I have already said in the lecture 13. In lecture 14 we will see how to use the polar chart. So to facilitate learners to use the polar chart, anyway the polar chart is not at all required for doing the problems in Nyquist stability analysis, but still if one is interested how to use the polar chart, then this particular explanation will definitely be useful for understanding the same. For example, I have this tabular column for variation of magnitude and phase angle with respect to the frequency. So here I can find that magnitude is varying from 25 to 0, phase angle varying from 0 to minus 180, when omega is varying from 0 to infinity. This particular chart is called polar chart. In this polar chart, we have angles from 0, 10 degree, 20 degree, 30 degree, 40 degree, all that. So for that angle, I have radial line 0 degree, 10 degree, 20 degree, 30 degree, 40 degree, like sun rays. So we have different radial lines for different angles, right? Then we have a lot of circles, circle. So circle represent the magnitude, and radial lines, this is angle, circle is the magnitude. Now 1, 2, 3, 4, 5, 6, 7, 8, some 8 circles are there. So this is the origin or 0. So one circle, one big circle, I am taking magnitude of 5 because I have to accommodate 25. That means 1, 2, 3, 4, 5. So this fifth circle corresponds to 25 magnitude if for the scale that I have taken. Therefore 25 0 means along 0 degree at 25 I have to mark, so I have marked. Then at 0.2 radian per second, 24.39 magnitude and minus 17 means, see this is 10 degree line and this is 20 degree line means, so somewhere here it will be minus 17 degree, 0, minus 10, minus 20, because clockwise means negative angles. Minus 17 degree I have to have 24.39. So it is closer to this fifth circle, but here, so I have marked. Then 21.69 minus 40.6. That means along minus 40, this is 40, minus 40. I have to have 21.69. That means 4 circle means 20. Then some 0.2, 4.2, something like this. Then 15.81 minus 17.57. What is 15.81 minus 17? Minus 71 means minus 72. This is minus 70, minus 80. So minus 71 will be somewhere here. In that 15.81 means 1, 2, 3 circles, some 3.2 circle here. Similarly, I can mark for minus 146. So this is this is 71. I'm sorry. Next minus 108 degrees. So minus 100 minus 108 is here. So minus 108, 7.91. 7.91 means less than 2 circle, because one circle is so here. One circle, this is 2 circle, right? Then at 5, 1.82 minus 146. So minus 140 is here. Minus 150. So minus 146 is somewhere here. And I should mark 1.82 means less than one circle, big circle only here. Now I have to join all these points with a smooth to freehand curve. I will do that. So if I join all the points with the smooth to freehand curve, that is actually my polar plot. That is nothing but my mapping of C1, right? I am joining all these points. Here I have not mentioned about these things because their values are very, very less. So omega 0 to infinity. So this is your omega equal to 0. And this is omega equal to infinity. Suppose I want to do mapping of C2 means exactly this I have to do the mirror image. That's all. So that you can do. Anyway, this I have done only for understanding how to use the polar chart. So this particular presentation, lecture 14, I have explained very clearly the use of Nyquist stability criterion for condition stability problem, and then if I have special case where I have singularities, that is Nyquist contour should not pass the singularities, therefore how to indent it and map it. Then very important thing, what is the gain margin, phase margin, how to determine the gain margin, phase margin, that we have seen. Then how to use the polar chart for doing the problems in Nyquist stability analysis. So this way we can do use polar chart for any problem. However, it is not compulsory to use the same. Thank you.